Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B electric circuits practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe, it really helps our channel. So this is the problem that we're going to be solving today. We are experimenting with circuits in DL. We have 3 light bulbs and a battery. When we build the circuit shown here, we find that the brightness of light bulbs 1 and 3 is the same, and light bulb 2 is twice as bright, double the power as light bulb 1. We know that light bulb 2 has the resistance of 4 ohms, and we have to find the resistance of light bulbs 1 and 3. Show your work. So as you can see, I have everything written down here. So I have the 3 light bulbs and I have all of the information. 1 and 3 same brightness, 2 is double the amount of power, and then I also copied my equations for power across a resistor over here, because just by looking at the instructions, it's very obvious to me that at some point I'm gonna need them. Oh, there's hair everywhere. Okay, so the first thing that I'm gonna do is figure out how the current is flowing on this circuit, because the battery is over here in the middle. So let's just go ahead and define some currents. So the total current is always the current that's crossing the battery, and we also have 2 junctions. So our current is definitely gonna split up. So we have a total current crossing our battery, and then the current is actually gonna split up. One current is gonna go upwards over here, and then one current is gonna go downwards over here. So let me just draw them. So we're gonna have a current over here. I'm just gonna call it, say I1, because it's crossing resistor 1. And we also have a different current that's, this one over here. And this is, I'm gonna call it I3 because it crosses R3. And okay, so this current actually starts over here. So maybe let's just be clear about that. So we have green hits this junction, and then out of this junction goes blue and orange like this. And then in this junction, blue and orange are gonna recombine, and then green is gonna get out of here. So my continuity equation for this junction is gonna be that I total is equal to I1 plus I3. So now that I have that figured out, I need to look into these conditions. 1 and 3 have the same brightness. So 1 and 3 are, not at a glance related to each other in terms of voltage and or resistance, because they have completely different currents crossing them, and also their delta V is not the same because this resistor has another resistor in series. But we do have this information over here, and we also know that, whatever amount of power these 2 guys have, this one has double that. So I think that what we need to do is start by combining these 2, or well, not combining them, but like sort of using this one to figure out what this resistance is, and then build our way towards this lonely resistor over here. Now we know that, just grab green, the power dissipated by resistor 1 is related to the power dissipated by resistor 2. 2 has twice the amount of power. This means that you need 2 1s in order to make 1 2, like this. So this one is twice the amount of this one. Now I need to figure out which one of these guys I'm gonna use, because obviously if I'm giving this information, then I want to use it, right? So I think that the easiest solution by far would be to use this equation over here, because both of the resistors are being hit by the exact same current. And whenever we're using these equations, we need to use the current that is hitting that particular resistor, or the voltage across that particular resistor. Now these two resistors are in series, and by definition, whenever two resistors are in series, they have the same current but different voltage drops. So I'm gonna go ahead and use this one on the merit that they have the same current. So if I do something equals to something, then that means that I'm probably gonna be able to cancel it out. But let's just go ahead and do that. So this is 2, and then I'm gonna substitute this equation over here. So this means R1 I1 squared, and this is equal to R2, but here we go, and this is the useful part. R2 is also being hit by I1, so I get to do I1 squared again. So basically these two guys are gonna cancel out. So we have 2 R1s are equal to R2. So R1 is equal to R2 divided by 2. And we do have the value for R2, which is equal to 4. So this is just 4 divided by 2. So R1 is equal to 2 ohms. Final answer. There we go. So this is 2 ohms. This is 4 ohms, like this, which means that you know, in terms of voltage drop, they don't have the exact same voltage drop, but because this one is exactly twice as this one, then we know that delta V across R1 is half as much as delta V across R2, like this. Just because of the values of the resistances. How do I know this? Well, you know, as a side note, remember that delta V across a resistor is IR, like this. Both of the resistors are have the exact same current flowing through them. So whichever has the higher resistance has the higher voltage. Now, one resistor is exactly twice than the other. Well, that means that that resistor is dropping twice the amount of voltage than the other. So this means that because R2 is greater, then you need to, then is dissipating twice, you know, the voltage. But anyway, so let's just move on. So let's see. Now for R3, we have a little bit of a situation, because we could try using this equation over here. However, we obviously need a way. So the problem that we have over here, and this is sort of like what makes this a challenging problem, is that we now have all of the information, you know, regarding the lower branch, but like this branch is completely separated. So what we need to do is sort of like figure out how we can use the info over here and sort of like in order to solve this over here, right? So let's see. First of all, I know that this guy and this guy over here have the same power. So let me just start by writing that down. So let's see. So let's just try working things out. So the power dissipated by 3 is exactly the same as the power dissipated by 1, because they have the exact same brightness. So this is one of the connection points, right? So now let's see what else we can figure out. Now, let's use delta V. So delta V across resistor 3, you know, square, because it's a square divided by resistor 3, has to be equal to delta V across resistor 1 squared again, but now divided by resistor 1. Resistor 1 we already have, so this is not a concern. The only thing that is, you know, preventing me from finishing this problem is that I have this number, this is what I want, but I need to figure out a way in which I can maybe relate these two. because I can't just cancel them out like this. They are different numbers. However, if I can figure out a way of connecting them, then I can substitute and then I can cancel out. For this one, it was very easy because if it's the same current, then I can just cancel it out. But obviously, I'm gonna need sort of like an extra step over here. So I need to figure out how these two are connected to each other. Now, the way in which they connect to each other is by, you know, if you use the loop rule, you can see that delta V1 plus delta V2 has to be equal to delta V3. And this is how they connect. Well, how do I know? Because you can use your loop rule on this lower branch, and you can use your loop rule on this upper branch, and you'll see that, you know, because these two branches are in parallel with each other, like this entire branch and this entire branch are parallel to each other, they start at the same junction and they end at the same junction, then they need to add up to the same voltage, which would be the battery actually. But now, if I just substitute this over here, then that's not really going to be useful. If I substitute these two guys over here, that's not going to be useful because I'm not going to be able to cancel things out. I'm going to be able to cancel B1 out, but I'm not going to be able to cancel this term. And also because this is squared, I would have like a complete mess going on. So what I need to do is figure out how to simplify this and maybe come up with an equation in which I only have B3 and B1. Now, how do I do this? Well, this is where this part is gonna actually be handy. So it was, you know, it was worth figuring this out after all, even though I didn't know if we would have to. Because if I substitute this equation over here, then what I'm gonna get is delta V1 plus 2 delta V1s is equal to delta V3. So 3 delta V1 is equal to delta V3. And now I can use this. This is actually going to be very helpful. So I'm just going to put it back over here. Yes, so this is actually going to cancel out because see, so 3 V1s is equal to 1 V3, so I'm just gonna substitute over here. So instead of a delta V3, I'm gonna have 3 delta V1 squared divided by R3 is equal to just delta V1 squared and divided by R1. Now, now I can actually cross out delta V1 because we have the exact same number squared. So this guy cancels out, this guy cancels out. The only thing that's going to be important is that this this squared is gonna distribute. So delta V1 squared cancels out, but this is a 3 squared, right? So this is actually a 9. So 9 R3 is equal to 1, and then R1 is equal to 2. So R3 is equal to 2 times 9. So R3 is equal to 18. Almost final answer. There we go. So this is our final answer to problem 1. So now let's see. Part 2 says you add a wire across light bulb 1. Describe what happens to the brightness of each light bulb. Gets brighter, gets dimmer, stays the same, or not lit compared to the original circuit. Explain. Okay, so on this circuit over here, basically what we are doing for part 2 is we are going to take a wire, R1, yeah, light bulb 1, and put it over here. So now what's gonna happen? Well, remember that when we connect a wire in parallel with a resistor, what we are doing is basically shorting out this resistor, which means that all of this current over here that used to be I1, instead of crossing this resistor, we're adding a junction over here, And once this orange current gets here, it's gonna have to decide whether to cross the resistor or just cross a wire. And whenever we have a bare wire, the entire amount of current is just gonna go through the wire, because this is a path of no resistance versus a path of some resistance. Now, whenever you have two paths with some resistance, the current is gonna split up proportionately. But if there's ever a path of no resistance, then that is completely different. And whenever you have at least one path of no resistance at all, then 100% of the current is gonna go through this path over here. So now, by doing this, then basically what's gonna happen to R1 is not gonna, it's not bright at all, so it's not lit. So R1 not lit, because if you don't have any electricity flowing through the light bulb, then obviously the light bulb is de-energized. It's not energized, that's better. So it's obviously not gonna light up. So now we have to figure out what's gonna happen to the other two. Now R3 is actually very easy to figure out, because R3 is completely independent to what is happening in this branch over here. So R3 by definition is, delta V squared divided by R. Delta V squared is just gonna be whatever amount of voltage this battery is supplying, because if you do a loop rule, you'll see that delta V is just, this E value over here. So because we didn't change the battery, delta B for R3 is gonna stay exactly the same. If delta B stays exactly the same and we didn't do anything to the resistor, then nothing is gonna happen to R3. So stays the same. Like this. So now what is gonna happen to R2 would be the question over here. Now what's gonna happen to R2 is actually interesting, because we have to figure out whether it's brighter, whether it's not lit, or whether it stays the same. Now some things have definitely happened over here. So you short out this resistor over here. If you short out this resistor over here, then what's gonna happen is that now all of the voltage on this branch over here, the voltage used to be split up over here and then over here, but since this element is not operational anymore, it's de-energized, delta B has to increase for R2, because now instead of dropping some of the voltage, R2 is gonna drop all of the voltage. So for R2, delta V is actually going to increase, and because this number is going to increase, then R2 is actually going to be brighter. And this is going to be our final answer for part B. So now let's see what part C is. So part B. So part C is, you recover the original circuit by removing the wire you placed in part B. Okay, so now this wire doesn't exist anymore, but suddenly light bulb 1 burns out. Describe what happens to the brightness of each light bulb in this case. Gets brighter, gets dimmer, stays the same. Okay, so now basically I'm gonna redraw my circuit. So what's gonna happen over here is that, we have our battery like this, but now instead of having this one, it burns out, so it basically looks, so this is R2 and this guy is still R3. So like this, whenever a resistor burns out, it's just basically an open circuit, so it means that no electricity is flowing through it anymore, and this is very different than shorting out the light bulb. So this is a short out, and this is a burnt out. So whenever So once this light bulb burns out, the current is not going to be able to flow through this branch at all. It's not going to be able to flow. So that means that, you know, first of all, R1 is broken, so R1 is not lit at all. Obviously, if you burn out, that means you're out of business. R2 in this case is also not lit, because if you can't complete a loop, if the electrons can't loop like this, then this means that there are no electrons consistently, you know, there are no charges, because we're working with charge. There is no charge flowing through here, and because there is no charge, then, you know, this one is also not lit. Now R3, of course, is different, because R3 is its own little branch, and actually you do have a current flowing through R3 like this. And R3 is basically going to stay the same for the exact same reason that I used before. By definition, P3 is delta V3 squared divided by R3. The resistor stays exactly the same because I didn't change it, I didn't burn it out, I didn't short it out or anything. And delta B, if I do a loop rule over here, delta B is still gonna be just the value that this is supplying. So nothing is really changing if I didn't change, well, nothing is really changing for R3 if I didn't change the battery or this resistor. So nothing is really changing in this branch, so that means that R3 is just gonna stay the same. So basically we are done with this problem, so I hope that it was useful. If you have any questions, definitely let me know in the comments, and I'll see you guys on the next video.